Hi, my name is Daniel and I'm a part of Team 1. Our team is working on Ollie. Ollie is a robot with a corresponding mobile app that is designed to help people in the event that they have fallen within a house. In the next two slides, I'll talk about how we've met our goals for Demo 1, and after this, I'll talk about the main progress we've made within the subsections of our project. This entails progress on the user interface, hardware, and software. We have met all of our goals except for one. This slide shows the goals that we have met for this demo. For this demo, we've achieved setting up a good workflow for the team by setting up the simulation environments and code sharing facilities. We have also completed research on the main components of our system and have reached conclusions on how to proceed for the rest of the project to best meet our goals. However, there is one particular goal we have not fully completed. We have not yet fully devised a method of fall detection for our robot. The fall detection component of our robot is responsible for detecting when a person has fallen down. We have considered different approaches, from using computer vision within the robot to using an external wearable device. The conclusion we came to was to use a mobile app. A mobile app would allow us to leverage the gyroscope and the accelerometer of the corresponding smartphone. The task is listed as partly achieved, as the team has yet to decide on the exact mechanism for detecting falls via the smartphone. As a result of our research, we have decided to use a Turtlebot Waffle Pi alongside an Xbox Kinect sensor. We have decided to use the Kinect sensor since it is cost-effective and it enables us to use localization and mapping for the robot's autonomous movement feature. We have decided to use a Pi on board our Turtlebot, as it gives us the ability to compute the mapping and motion of the robot. A custom manufactured frame is something that we are currently researching. The material of said frame is yet to be decided upon, since we are still deciding an optimal cost to strength ratio. Our current selection of material options that we are exploring are ABS plastic, 3D printed, carbon fiber, and wood. We have created the user interface that the user will interact with. Currently, we have two buttons. One is to call Ollie, which when pressed will call the robot to the user. The other button is used to set up the app and robot. Clicking this will lead the user to another page where they can configure the app and robot settings. I will show an example of this at the end of the video. There were important decisions taken for this part of the project. These are centered around making the app have high usability, since our target audience of the product is the elderly. For example, one consideration was to use sans serif or serif fonts. A serif is a decorative stroke that finishes off the end of a letter's stem. From our research, we found it is generally accepted that, for web and mobile applications, using a sans serif font increases readability. More detail on this and other considerations we took can be found within the report. For the reasons mentioned here and in the report, the font chosen in the prototype is called Yaldavi Colombo. For the software part of our system, we have researched algorithms for autonomous navigation and mapping. We have decided to use SLAM. SLAM is the abbreviation of Simultaneous Localization and Mapping. SLAM is a method used for autonomous vehicles that lets you build a map and localize your vehicle within that map at the same time. To integrate SLAM into our system, we are going to use ROS. ROS is a flexible framework for writing robot software. Within ROS, there is a package that allows us to utilize SLAM within our system. There is also a navigation package within ROS that would allow us to solve obstacle avoidance and route planning between 2 points. I will now go on to present our progress of the UI in the form of a video. There are 3 buttons on the home screen of the app: Call Ollie, Setup, and Full Sensor Demo. Clicking the Setup button brings us to the following page. The setup of the app requires your name, age, and where do you live. Using this information, we can show the user the closest hospital to them. You can also provide an emergency contact with their name and phone number. The next stage of the setup requires the user to connect Wi-Fi and Bluetooth with Ollie. Once a connection has been established, Ollie will now start mapping the house, and when done, a blueprint will show up on the app. This is an example blueprint which shows what can be expected in the future. Let's now return to the main page and explore the other buttons of the app. Pressing the Call Ollie button will summon Ollie to the user. Once Ollie finds the user, there is an option to call the emergency contact. In the future, the robot will be able to help the user stand up by providing a sturdy frame to hold onto. Another future feature is that the app will be able to detect when a person falls over. In this case, the app will call the emergency contact in 1 minute and Ollie in 15 seconds. The user can cancel either of these with a click of the button. I'll now go on to present our progress of the hardware, the Turtlebot Waffle Pi. During initial simulation testing, we found that the Turtlebot was easily able to change directions when approaching a wall or a large obstacle. This can be seen in the current videos. The robot is seen approaching an obstacle, pivoting and turning away and continuing its journey. However, it has been found that the robot struggles when it comes across smaller objects like a table leg. This current video is an example of this. You will see how the robot struggles to deal with this table leg. We believe that this is because the ePuck is smaller than the Turtlebot and thus is able to navigate past smaller objects. This means we will have to make some changes to the ePuck controller to better suit the needs of our Turtlebot. That concludes our presentation, so thank you for listening.